Hello, everyone. Excuse me. So in this video, we will go through an example of beam analysis using Abaqus over here. As you can see here on the screen, and there is a beam and under uniformly distributed load, 50 pounds per foot, as well as a concentrated load. As one of the quarter point over here. So now let's see whether we can use Abaqus to analyze this beam. Definitely we can. And yeah, the material type of this beam is given. This is steel 30 times 10 6 order psi. That's the modulus of elasticity, and the shear modulus is also given over here, and the cross-sectional dimension is also given. So it's 2-inch deep and 5-inch high. So I believe that the width is 2 inches and the height is 5 inches. Right? So that's why we can calculate the moment of inertia about the strong axis and the moment of inertia about the weak axis. So we are required to determine maximum deflection. So under the load, the beam will be deflected. So we should be able to calculate the deflection, maximum deflection, as well as the stress. The stress is so because it's under bending, so one side is under tension, other side is under compression. We should be able to calculate the maximum bending stress is in both tension and compression, right? So we are required to use 8 beam elements. So we divide this to 8 beams, and we can also compare our results with beam theory. Beam theory and deflection is given in the tutorial document over here. I believe this is based on the Bernoulli theory. If you use the Timoshenko beam theory, the deflection formulas will be a little bit different over here. So now let's start Abaqus. So here I have my Abaqus open over here, and the first step, similar to other. Better to move my. Okay, so the first step, we better after you open the Abaqus as a habit over here, or as a routine, and I typically I would set the work directory over here. So set work directory. So as you remember, the default one is the C drive tab, but I would like to have it in my personalized, customized. It's personalized, so it's under my course. So it's online course tutorial 2. So this is the first step. So as long as we are done the setup of the work directory, hopefully, some of you could do the similar step to make sure you set up your work directory before you do any analysis, so that you know where to find the files you need over here. So now let's draw the sketch. We go to the sketch module over here. We draw that sketch. So it's a beam, and so we basically draw a line, but we need to apply a load. This third quarter point over here. So we better to draw 2 lines. So one is for the 15 length here. The other one is for the remaining 5 foot over there. We show. Please keep in mind that anytime when you do analysis using Abaqus, you need to specify your unit system here. For example, in this tutorial, we use pounds for forces, and we use inches for length over here because the modulus of elasticity is given in pounds and inches, and the moment of inertia is in inches. So it's better for us to use inches for the length other than the feet over here. So we have the 180 inches and the 240 inches for the whole length there. So we can just go ahead, start at a peak point, start draw the lines. So 0, 0. This is the first one. Second one is 180, 0. The last one is 240, 0. So when you are done, you can just click the cancel, and then we are done. So we are done. So we have the sketch over here. So or you can have a name, and what name does you can have a name, or you can just use the default one. Okay. So so this is the sketch that we have. Now we go to the part. So we create a part from the sketch. So we create a part that's a two-dimensional, deformable. It's a wire. Continue. So you may draw that geometry over here, since we have already had a sketch. We can add the sketch over here. So the sketch is already here. So we show over here. So everything looks good. Everything looks good. So we are done. And then we are done. So everything. So we have the beam already here. The beam already here. Please keep in mind to solve your file. Solve your beam. So that is beam model. Just use beam model over here. So this is our file. Beam model. Next step, we go to the property. We input the material as well as the cross-sectional property. So first step, we create a material that's steel. So we go to mechanical, Young's modulus. So that's 30 times the 6th order. So this is modulus of elasticity. And how about the shear modulus? We are given the shear modulus. So we need to calculate the Poisson's ratio. Actually, there is a relation between the shear modulus and Poisson ratio. We can just go ahead and input 0.3, and as specified in the tutorial here. So that's 0.3. So this is the modulus of elasticity as well as the Poisson's ratio. We click OK. Okay. So next step, we define the section. So we will have a beam section. It will be a beam. Continue. And as long as you open the beam section definition over here, and before you do anything, and we need to create a beam profile, such as the shape of the cross section, whether you will have a I-beam, a rectangular beam, or a circular beam, and you can define this. In our case, we will use the general beam. We create a generalized. So the area is given as 10, 20, so we just input the numbers showing here. So that's 10, 20, 83, I11, I12, that's 0. So, and I22, 3.3333. And the J, that's for torsional resistance. Since it's a 2D problem, we don't care about the torsional movement. So I think all the inputs are pretty good here. Okay, so we need to change everything to the pro analysis. During analysis cannot do. So we before do that, and we profile one is generalized, so everything else pretty much the same, and we can also input the Young's modulus here since it's not got linear property. Have the Young's modulus, so 30, and shear modulus is 11.45, and we are also required to give output points. So that's the top and the bottom of the beam, right? So that we can have the centroid, pretty much nothing changes here. Young's modulus and the shear modulus, let's say 11.54. So that's the shear modulus, and yeah, I think material type, or we can just go ahead to use the material name here. Either way, I don't think that way they'll have the same number. Specify material density. We do not need anything here, and output points. We would like to have the output points for the top and the bottom. Top and bottom. So we have the minus 2.5 and then 0, 2.5. So this tells us the stress output will be for the bottom of the beam and the top of the cross section here. So I got it correct. Click OK. So everything is defined for the beam section. So next step, we assign the section to the beam. Select all of them, and selection 1. We're down here. And we also need to assign beam orientation, because since you have a cross section defined here, the cross section can be oriented in two options. Option 1, you will see. So we define the beam orientation. Keep the default. So this is the default one. Defaultly, the strong axis will be the same as the global axis over here. We just keep as it is. I believe that, yeah, keep it as it. Click OK. So we are done with the assignment of properties to this beam. And then we go to the assembly. We create dependent or independent. Probably with this one, we just create a dependent one. Dependent one. Click OK. So yeah, so the model has already been created as assembly here. So we just save everything. Step, create a static step. So nothing to change over here. Then go to the load when nothing, and to define for interaction over here, because there is no interaction. So load, we have simply supported. That's one, 2 ends, and we have the load. First, define the concentrated force. That's in this point. So that's minus 5,000. Minus 5,000. Minus 5,000. Or you can define the line load firstly. That doesn't matter. Minus 5,000. So we have minus 5,000 force, and then we define a line load per 2. That's along the full length. select both of them by press the shift button and the uniform component, that's -4.16. Please keep in mind to convert the distributed load to a value in pounds per inch. So this is the uniform distributed load. We have everything here. Next step, we apply simply support. So this is a pin support. So it's constrained both X and Y. And then the other side, we have a zoner support here. Constraint to so we save everything, and so we'll have the support here, and then we have everything already. Everything already here. So then we go to the mesh. We would like to have let me follow the. So we would like to have element size 30, since we define the number of we have 30 inches, and then we have the beam type. The first step, we assign dependent cannot be added assign mesh attributed. So make it as independent. Make this as independent. Make it as independent. Now we assign the size to 30, so that we will have 8 in total. So let's count it. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 in total. Now we assign the element type for all the material. It's beam type. We have 2 types. Either the B21, so it's a shear flexible. That's Timosenko beam. And then we have cubic formation B23. That's the Ola Balloni beam. We will use the B23. So I click OK. So the beam type has already been assigned. Next step, we just do the mesh. Just do the mesh the instance. So you can see here the color has already been changed from purple to light blue over here. So everything is meshed. So up to here, we are done with the modeling, including the geometry as well as the mesh element, materials over here. Next step, we go to the job. We submit a job based on this model, as we do not do any changes here. So it's pretty much a linear, simple analysis. Then we can open the job manager over here. We submit it. It takes a few seconds here. Yeah. Now it's completed. So now we can go to the result. So this is the beam. This is the beam. We can show the we can change the color to white. Similarly, or we can show the element labels here. So firstly, let's change the graphic option. We change the background. Just use a solid background. Change everything to white. So have a white background, or if you would like to have a black background, you can do that too. And here we can also show the labels, such as the elemental labels and the load labels. So probably a black background will be easier for us to see the colors. change it to black. So this is that if we have a blackboard here, it's easier for us to see the colors instead of white. So we have everything. We have the node numbers as well as the element numbers here. So next step, we can show the deformed shape. Right? We can show the deformed shape. The underload, this is a deformed shape. Right? We can also show the stress. Right? The stress 1, that's the bending stress. We show the stress. Plot contours, deformed shape. So this is a family stress. So we show the bending stress and the bending stress. As you can see here on the legend on the left corner over here, so that's the coordinate for minus 0.5. Minus 0.5. That is for positive numbers. I can just go ahead. The result we would like to uncheck the averaging here. So since here, so we can show the stresses there. Stresses here. So that's the bending stress coordinates minus 2.5 and 2.5. Everything is showing there. Y in the. Okay, so we go to the options. Okay. Also plot. So the only thing here in our case, only the negative value, negative 2.5 is shown here. But it's okay. Can select the coordinates, both the coordinates here. So unavailable, we can select section points. Section points. Can select the positive. Okay. It looks like in our case the positive means that we have the tension and the compression. Tension and compression both. Can we show both of them, top and bottom? Yeah, we can show both of the top and bottom. Top and bottom, both of them are shown here. That's the bending stresses. It's the bending stresses. So yeah, so we can output the result here too. Output. So we can report the field output. So for example, if we would like to show the displacement in the deflection value, so we can go ahead to that, apply the load. So it's showing the Abaqus now. We can also the data file now. We can also show the stress component, the section points. Can select the stress S11, the section points. It's default here. No showing here. Probably for stress, would better to use the integration point. No, fundamental node. Not here. Okay. If we like to show the element node, okay. surface. Okay, let's show the stress firstly. See whether everything's stored. Let's go to the Abaqus. So as you can see here, anytime when you do a output, when you output the results, the result will be output. So every new data will be appended to that older data over there. Firstly, we show the deflections. As you can see here, the maximum deflection is given. As here. Oh, so minus 1.873. So it's pretty the same. Then we see the S stresses. We also show the stresses. In the location 2, we have the positive values, that means tension. Negative means the compression. We have the maximum tension, that's 29. It's in node 2. That's in node 2. So that's the same. That's the same node 2. Node 2 here. So up to here, we should be able to get the maximum bending stresses in both tension as positive values and the compression in negative values over here. So that's a beam analysis. We are interested in the deflections as well as the bending stresses at the bottom and at the top of the beam section over here. And for civil engineers, I probably wanted to know the shear and the bending moment here. So let's see whether we can the bending and shear. So have the concentrated force, have the reactions. So the internal forces at minimum are not shown here. So we'd better to go back to the output. Say define the output. Say so as you can see here, forces and directions concentrated in those are the applied force. See whether we can output any nodal forces. Either nodal forces or sectional. I think nodal forces would be okay, since if you have the nodal forces, you can tell the bending moment and the shear. Or we can have the section forces and the moments. So section forces and moments, everything will be sectional. Okay, so then we go back to job, resubmit the job, so that we can see whether we can have the bending and the shear values. Okay, so it's all completed. So we'll go back to we reload the data, see the shear sectional force. That's F1, and it could be the axial force, shear moment. So this is a sectional moment. SM1 beam stresses. Okay, so let's do sectional moment on the cell. So that's sectional, and this is bending moment along the length. And let's see whether we can show some some lines. Okay, and quilt. No, it's not showing. What? It's not. So it shows some values here. That's a. We can show that's the bending moment. That's the bending moment. That's pretty much similar as you. So we have a zero on one end, zero on the other end, and this is the bending moment. The shear force looks like the shear force is not showing here. Yeah, the shear force is not showing here, unfortunately. But we can try the load forces. Go back to the step. We recreate the. We just show the load forces. So the load forces due to element stresses. Load forces in beam section orientation. Let's see what we will have in this case. So we resubmit it. So it's completed. So we dismiss it. So go to the visualization, reload the results here. Let's see some. So this is misses stress. We would like to show the. So we have the nodal force 1. I believe that's axial force. Force 2, that's the shear force. So yeah, here we have the shear force diagram. And then we can also show the bending moment diagram. I think the nodal force give us a better interpretation of the shear and bending moment diagram. So this is the shear diagram, and this is the moment diagram, and then we can also show the maximum values. Show the maximum values or minimum values. We show location. Show location. So the maximum value is pretty close to 0. The minimum value. So that is maximum bending moment. We can also have the maximum shear. This is the. Oh, it's not showing us. This is a 0 load of force 1. You can just go check this. Load of force 1, there are some load of force 1. Oh, so since we have two loads there, there's two nodes there, so we have the load of force both ends. So this is a bending moment. This is a thing. Why don't we have the shear diagram anymore? Sectional force. I think sectional force would be more appropriate here. I have the load of force. Anyway, we can try the other option of field output. We can try the action forces. We can export the values to field output. Let's see. Try another one. We go to the step. Now we show the edit. So nodal force due to element stresses. Let's see whether we can have the element stress values. We can compare that. the result here. So we have the job, resubmit the job here. As you can see here, there are so many different types of outputs here. So in order to be clear which is which, you'd better to refer to the Abaqus documents here. So we show the results here. As you can see here, we have the nodal force. So this is I don't know. Let's say we have the two tick marks. This is some nodal force 1, force 2, nodal force 6. Every time it shows. Okay. And so this is the nodal force. I think this is a better illustration of the bending moment here. And this should be shear, but it's not showing the diagram over here. But we can do this is nodal force 1, nodal force 2. Right. Okay, it's not showing here. Here it's not showing, but we can do the output. We can just go ahead, output everything to see which one gives us better result. Just go back to the output file. So we have everything is below here. So for each of the load, we have the shear forces as well as the bending moment here. Yeah, bending moment. I believe, yeah, the nodal forces and nodal could be a better representation here and representation. So that's that. So we should be able to find, anyway, we should be able to find the maximum bending moment as well as the maximum shear force from the analysis data over here. So you can compare the numbers with the theoretical values too. I think that's all for this video, and good luck to your practice with this tutorial, and thank you.